Hello everyone, I'm Sabyasachi from the Indian Institute of Science, Bangalore, and I'll present our team's work, DSLR, Dynamic to Static LiDAR Scan Reconstruction using adversarially trained autoencoder. This work was done in collaboration with Motors. Autonomous navigation is an open area of research with exciting applications like self-driving cars. Critical to this is the generation of city-scale maps of the environment. Here we can see that the LiDAR scans captured on a highway can be used to generate 3D maps of the city, which are critical for the self-driving cars. But most autonomous navigation algorithms assume a static environment. Hence, real-world use cases corrupted by dynamic agents hinder the performance of state-of-art algorithms for robot autonomy. Let's consider LiDAR-based SLAM in dynamic and static environments. The left image shows the map generated in a dynamic environment, and the right image shows the map generated in static environments. We can see that the map generated from dynamic scans contains many corruptions than the map generated from static scans. Therefore, we can see that the autonomous navigation algorithms like SLAM are much better in a static environment than in a dynamic environment. We attempt to solve this problem by transforming a given dynamic LiDAR scan to a corresponding static LiDAR scan. Before we go further, let's look at a sample dynamic and static LiDAR scan. The LiDAR sensor at the center captures a 360-degree view of its surroundings. Throughout our presentation, we follow the convention that red in a dynamic scan depicts the movable agents in the surrounding. The static LiDAR points occluded by dynamic objects are also represented as red in corresponding static LiDAR scans. We pose the problem of dynamic to static translation for LiDAR scans. We seek to learn the mapping M from dynamic scans to the corresponding static scan such that the reconstruction loss is minimized. We focus on two major goals here: accurately reconstructing the static structures like walls or poles, and inpainting the occluded regions with static background. DST for images and object point clouds have been explored as shown here. The left image denotes an existing work that presents an end-to-end deep learning framework to turn images with dynamic content into static frames. However, this work uses segmentation information for dynamic objects, which is hard to obtain. Another related work on shape-based point clouds is shown in the image on the right. The technique primarily addresses scan completion, employs an unpaired and unsupervised strategy to complete partial point cloud scans. But their method, when adopted for LiDAR scan completion, fares poorly. This is the closest work that relates to and can be adapted to our problem and uses generative modeling to reconstruct and generate LiDAR frames. However, the reconstruction obtained using this work fares poorly when used for SLAM. But merely applying the existing works for our problem statement has the following limitations. Existing DST works explicitly require segmentation information, which is often hard to obtain in a new environment. The shape point cloud based scan completion methods also do not work when adapted to LiDAR point clouds. Finally, these methods fail to generate high quality reconstructions, which are very important for downstream autonomous navigation tasks like SLAM. We address these problems in our work and make the following contributions, which can be majorly divided into three key parts. First, we propose DSLR and its variants to solve the problem of DST for LiDAR. Next, we propose a novel dataset generation algorithm to generate dynamic static pair dataset in real world. Finally, we demonstrate our proposed approaches are currently the only feasible LiDAR reconstruction methods that can be used for LiDAR-based SLAM. Now we'll go through these contributions in detail throughout this talk. We propose DSLR to solve DST for LiDAR scans. DSLR employs three modules. The first module is LiDAR frame autoencoder based on DC GAN, trained to reconstruct static and dynamic LiDAR frames. The second module is pair discriminator, a multi-layered neural network trained to discriminate LiDAR scan pairs. It outputs 1 if static-static pair is presented as input and outputs 0 if a static dynamic pair is given input. The third module is an adversarial module, which combines the above two modules using an adversarial strategy to fine-tune the autoencoder in phase 1 to translate a dynamic LiDAR scan to its corresponding static counterpart. For module 1, we train an autoencoder using dynamic and static LiDAR scan based range images as input. The encoder and decoder are adapted from the discriminator and generator used in DC GAN architecture. We use this trained autoencoder in modules 2 and 3 to train the pair discriminator module and the adversarial module. We train a pair discriminator that discriminates static-static pairs from the static-dynamic pairs. The discriminator is trained to output 1 when it is presented with a pair that includes both static frames. It outputs 0 when it is presented with a pair where the first frame is a static and the second is a dynamic frame. We use this approach over a simple static versus dynamic discriminator because we aim to learn what distinguishes dynamic scans from the static scan and focus only on the occluded regions in a dynamic frame for discrimination. Corresponding dynamic and static LiDAR scans look almost the same except for the dynamic occlusion. Given this dynamic and static frame structure, differentiating static-static pairs from static dynamic pairs helps the discriminator focus exactly on the dynamic occlusion. However, it is challenging to train the discriminator with this architecture because the latent vectors of static and dynamic LiDAR frames look almost the same except for the dynamic objects. Thus, it becomes tough for the discriminator to identify and the difference between pair R1, R2 and pair R3, R4. To circumvent the above challenge, we train this discriminator using a dual loss. Here, the pre-trained autoencoder is jointly trained with the discriminator. This ensures that the autoencoder can generate a latent representation that captures discriminative features of LiDAR scans as well, apart from learning the generative features captured during the autoencoder training phase. Using the dual loss ensures that the discriminator can easily distinguish between latent vector pairs R1, R2 and R3, R4. They now contain discriminative features to differentiate dynamic frame latent representation from static frame latent representation efficiently. In the third and final module, we combine the autoencoder and the discriminator in an adversarial setting. We train the autoencoder to give corresponding static latent representation for a given dynamic input LiDAR frame instead of dynamic latent representation. We use 2 copies of the autoencoder as shown in the figure. In this adversarial setting, all the model parameters are frozen except the encoder E alpha as shown in the figure, which is fine-tuned to generate a static latent representation for dynamic frames as input. The discriminator was trained initially to give output 0 for SI DW pair as shown in the figure. However, in the adversarial setting, we force an output label 1 for this pair and only adjust E alpha weights during backpropagation. This is done so that E alpha outputs a latent vector that corresponds to the corresponding static frame SW instead of the dynamic frame DW. The discriminator should remain non-trainable, or it might actually learn to give an output of 1 for static dynamic pairs, which is not desirable. We also fine-tune the encoder E alpha with reconstruction loss using the corresponding static LiDAR frame SW. This ensures that reconstructed static LiDAR frame preserves the static structures while only filling out the dynamic occluded parts in the input dynamic LiDAR frame DW. Unlike existing baselines, which also employ adversarial strategies, we work directly on input scans latent space instead of working on the pixel or image space. This works to our advantage and is one of the main reasons for the superior performance of DSLR. Here we compare our static LiDAR reconstruction qualitatively. Figure A denotes color dynamic LiDAR scan. Here red indicates dynamic objects. Figure B denotes the model reconstructed static LiDAR scan. Here, red indicates reconstructed static background. Figure C indicates the ground truth static LiDAR scan. Here also, red indicates ground truth static points corresponding to dynamic occluded regions. Let's compare the reconstructed static LiDAR scan in figure B with the ground truth static scan in figure C. We can see that the reconstructed scan can retain the static structures as shown in green and fills the dynamic regions accurately as shown in red in figure B. In real-world scenarios, corresponding dynamic static pairs may not always be available, and we propose DSLR-UDA to mitigate this issue. A model pre-trained on a simulated dataset usually performs poorly on real-world datasets like Kitty due to the inherent noise and domain shift in the target new domain. To overcome this, we use unsupervised domain adaptation or UDA for adapting DSLR to real-world datasets where paired training data is unavailable. Unsupervised domain adaptation applied on the model trained using simulated data can be seen on the right image. The reconstructed static LiDAR scan is better than the ones obtained without UDA. Lack of corresponding static scans for given dynamic scans of the Kitty dataset also makes it impossible to compare any DST algorithm's performance on Kitty. To solve this problem, we propose a new metric called LiDAR Scan Quality Index, or LQI. LQI seeks to measure the amount of noise present in a given LiDAR scan. For a poorly reconstructed LiDAR scan, the LQI model outputs a higher value and lower values for a well-reconstructed scan. We can see that LQI correlates well with the reconstruction error, and therefore we use it to compare DST model's performance on the Kitty dataset. We also extend our base DSLR method to improve static LiDAR reconstruction performance further if segmentation information is available. We refer to it as DSLR-seg. We use the base DSLR method to generate a complete 360-degree reconstructed static LiDAR scan for a given dynamic scan as shown in the top image. Next, we train a point segmentation model based on the famous unit architecture to identify all the scan's dynamic points. As we can see in the bottom image, the segmentation model has identified all the image's dynamic points as shown in red. As a final step, we only replace the red identified dynamic points as shown in the bottom image with the corresponding static points from the reconstructed static scan as shown in the top image. This merged static reconstruction is output from the DSLR-seg. This helps to preserve the reconstruction quality of the static structures perfectly. To generate a paired dynamic static dataset, we propose a novel dataset generation algorithm. First, we consider a random dynamic run and a random static run containing sufficient overlap between the runs. Next, we pair the dynamic LiDAR scan from the dynamic run to only the closest static LiDAR scan from the static run. We ignore all the pairs that have distances larger than a given threshold, say half a meter. This creates a pair of dynamic and static LiDAR scans. But all static structures between both the scans may not align perfectly. Therefore, all the static scan points are linearly transformed by the post difference between the two scans. This helps to better align all the static structures in both the scans. We can also use segmentation information, if available, to further improve the quality of the dataset generated. When we train the base DSLR model on this improved dataset, we refer to it as DSLR++, and it performs better than the base DSLR model. Next, we compare existing baselines with our proposed approaches. As shown in the last 4 rows of the table, we can see that our proposed approaches outperform all the existing baselines on all the LiDAR reconstruction metrics for simulated and real-world datasets. Now, we visually compare DSLR and its variants against the existing baselines. Figure A indicates the ground truth dynamic input. Figure H indicates the corresponding ground truth static LiDAR scan that we hope to reconstruct accurately using our models. We see that the reconstruction for our models DSLR and DSLR-seg, as shown in column 6 and 7 respectively, are quite accurate when compared to the ground truth static scan in the last column. Further, our reconstruction in columns 6 and 7 is also superior to the best performing baseline in figure C. Finally, we benchmark the performance of various static LiDAR scan reconstruction algorithms on SLAM. A typical SLAM setup is shown here. LiDAR sensor captures various 360-degree LiDAR scans. The SLAM algorithm takes this set of scans as input and outputs the vehicle's pose and environment map. Our LiDAR scan reconstruction models come in between the sensory input and the SLAM algorithm, like an input pre-processing step for SLAM. The scans generated by the LiDAR sensor are input to our models, and they output only static LiDAR scans for further consumption by the SLAM algorithm. Next, we experimentally try to determine what is the maximum LiDAR reconstruction error which can be tolerated by SLAM. As shown in the plots, initially, SLAM error or ATE increases exponentially with a linear increase in LiDAR error or chamfer distance, and then saturates at chamfer distance of about 2 meters. Therefore, any LiDAR reconstruction model with a chamfer distance of more than 2 meters cannot be used for SLAM, and we refer to it as SLAM reconstruction threshold or SRT. we can see that only our proposed approaches have LiDAR reconstruction error within the SRT threshold from the table. We also confirm this using localization plots generated by SLAM. The existing state-of-art LiDAR reconstruction algorithm fails to perform SLAM on a simple run of the Kitty dataset. However, our proposed approaches demonstrate high SLAM performance on very complex runs and perform competitively with existing SLAM baselines like detect and delete. Next, we compare existing approaches of handling dynamic SLAM against our model on both real-world and simulated datasets on widely used SLAM error metrics. We can see that our proposed approaches perform competitively with existing SLAM baselines, even outperforming them in many cases. Thank you for your time. Please refer to our project page for more information, open source code, and dataset.